As it has been mentioned before in the presentations, we know that remote sensing images provide very detailed information, but also result in very significant computational requirements. In fact, this has resulted in the fact that now we have several data repositories that contain several petabytes of data, and this imposes very significant requirements from the computational point of view, not only because of the amount of the data that we have available, but also because these data generally have very large spatial resolution and often also very high spectral dimensionality, like in hyperspectral data, where we can have images with hundreds or even thousands of spectral bands. The interpretation of the data is a very important problem, particularly in this section of the webinar. We are going to focus on the classification problem, which can be tackled at 3 different levels. We can have pixel level classification, as in this leftmost image, where we try to classify each pixel of the image into a different class. We can also have object level classification, where we consider the different objects in the image and try to perform classification in an object-based manner. And finally, we can do scene classification, like we try to assign a general label to the whole scene, like, for example, in this case, a parking lot. Now, focusing on hyperspectral data, there has been many deep learning techniques that have been successfully used for analyzing and interpreting the data. I'm going to summarize some of them. For example, the stacked autoencoder is based on the reconstruction between the input and the output. We have the original hyperspectral data cube. We feed every pixel in the original data to the encoder network. And then we have a decoder network that provides a kind of reconstruction of the original hyperspectral data. So this architecture has been widely used, for example, for compressed sensing or compressed representation of hyperspectral data. We also have the recurrent neural network model, in which the data cube is processed in a different manner, in band-by-band fashion, and the spectral signature of each pixel is processed as a temporal sequence. So we obtain as a result a hidden state that works as the model memory. Another very successful deep learning model, particularly for classification, has been convolutional neural networks, in which we process 3D inputs. That means that we not only consider one particular pixel, but also the neighboring pixels, the surrounding area. And then we can apply multidimensional kernels that act as filters for particular features. We can focus on borders, shapes, or other kinds of stimuli. In the end, we obtain a set of feature maps that will serve as the basis for the classification. In this case, generally we require training data, which is quite difficult to obtain in real scenarios. So we might be constrained by the availability of training data. Another famous model is deep belief network, which are composed of several restricted Boltzmann machines which process and reconstruct the input data. This architecture is somehow similar to the stacked autoencoder in the sense that we learn the probability distribution of the input in an unsupervised fashion. And finally, I would like to mention generative adversarial networks, GANs, which are also supervised and learn the joint probability between inputs and outputs, modeling the data distribution, to generate new samples rather than evaluating the available ones. This is very interesting because we can generate additional training samples when there is a limitation or a limited presence of them a priori. Now, how to implement these architectures efficiently, particularly if we want to run deep learning in distributed data repositories. As we have seen in previous presentations, the cloud is probably the best solution because either cluster computing or grids or even accelerators are more appropriate for real time or for data that has already been transmitted to Earth, but we don't have a lot of data to process. But if we have a large distributed repository, probably the cloud is the best solution because of the nature of cloud computing implementation. It is a distributed architecture which evolves from cluster computing and grid computing, but provides additional features which are very important for for our targets, such as scalability, elasticity, also heterogeneity is very important because we generally build clouds using different heterogeneous resources. We can also manage private and public services in the cloud. And particularly, we have a very powerful possibility for resource handling and allocation. So the cloud is generally considered as the most appropriate computing architecture for managing distributed repositories of data. In the cloud, we can apply the three traditional parallelization schemes, such as data parallelism, model parallelism, and hybrid parallelism. And the advantage is that we can apply a traditional master-worker approach, or the so-called MapReduced implementation, which is very popular and very simple to implement. So compared to cluster and grid computing, we have several advantages, particularly the way we handle the data and the fact that we can use the MapReduced model, which is very simple, and we can simply distribute the data among workers, and then the workers can cooperatively produce results independently or either communicate between each other, and then send results to the master node for final compilation of the final solution. I'm going to provide a very simple case study in which a deep neural network implemented on the cloud in distributed fashion is used to process a large hyperspectral image. And we are going to pursue a pixel-based classification. We are going to train the network, and we are going to provide a classification solution at a pixel level. This image has been already discussed in the first presentation. It is a quite complex data set with a size of more than 1 gigabyte and almost 60 classes. This is the Indian pine scene collected in northwestern Indiana by the Abri sensor. So we have used a very simple neural network, a multi-layer perceptron, and we have implemented it as a distributed classifier. The details are in the paper, but one important thing is that we can use this distributed implementation strategy to parallelize other kind of networks, like convolutional networks or GANs or other examples that I provided before. Here you can see the distributed implementation and also the different layers of our network. We have the input layer with 200 neurons, is the number of bands that we have in the spectral data. We have 3 hidden layers, and we have the output, which has the same number of neurons as the number of classes that we want to use for the pixel level classification. So here are the results on a simple infrastructure composed of 2 Intel Xeon CPUs with 8 cores and 160 gigabytes of RAM. This implementation could be expanded to more sophisticated platforms, but in the paper we provide just an example. And here you can see several kinds of results. For example, in this plot in the left, we show the run times as the number of workers increase. We can see that the run times are lower as the number of data becomes lower. So we have a scalability that depends on the dimensionality of the data. Of course, if we have more data to process, the runtime is lower and the speed up is higher. So that's exactly what we want to achieve when we use more workers in the parallel implementation. Another way to look at the results is to analyze the problem size. So we consider different problem sizes. Here we cropped the image, or we doubled or tripled the information to be processed, and we calculated the runtime and the speed up. One good thing that we can see in the result is that the speed up increases with the number of workers and also with the problem size, which is important because normally we would be targeting at processing very large data repositories where we not only have one image, but maybe a collection of images or several hundred images. So in conclusion, we can identify some remarks and future challenges. One is the growing importance of using cloud computing for distributed processing of remote sensing images using deep learning techniques, particularly when we want to run these deep learning architectures on distributed data repositories. This is of particular relevance because most of the remote sensing data that we have right now is big in nature and is stored in repositories that are not always located at the same place. For example, one single organization, such as the European Space Agency or NASA, could have several different repositories where the data are stored. And it might be very useful to be able to process all the data available with the cloud. In the future, it is particularly important to consider the inclusion and optimization of specific accelerators, such as GPUs, in the cloud environment. This has also been mentioned before in the presentations for deep learning-based remote sensing data processing and interpretation. And this is the end of my talk. If you have any questions, we will be happy to answer.